Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 20th, 2026, just 3 days ago. It introduces a video world model that responds to fine-grained head and hand movements, enabling users to perform tasks with over 71% accuracy compared to just 3% for text-only baselines. The paper is titled Generated Reality, Human-Centric World Simulation Using Interactive Video Generation with Hand and Camera Control. And as we'll see later, the system's ability to handle complex interactions in real time is really promising. Figure 1 illustrates the core concept of generated reality. On the left, we see the system's inputs, which combine a standard prompt, either a starting image or a text description, with real-time tracking data for head and hand poses. These 3D trajectories and hand models capture fine-grained physical movements that text alone simply cannot convey. The model then synthesizes the video strips shown on the right. For instance, the top strip generates a realistic driving scene where the hands on the wheel match the user's actual motions, while the bottom strip creates an imaginative alien landscape from a text prompt. Figure 2 demonstrates the system's versatility across a wide range of scenarios. The examples span from everyday interactions, like petting a golden retriever, to high fantasy settings like exploring a medieval dungeon. In each strip, you can see colorful skeletal lines overlaid on the hands. These overlays visualize the 3D hand pose conditioning, showing how the generated video stays locked to the user's actual movements, whether they are swinging a golf club or driving a car. Beneath each sequence, the text prompt provides the semantic context, which is enhanced by a large language model before generation. Well, Figure 3 details the architecture of this generated reality system. On the left, the pipeline starts with the user's headset capturing real-time data. The red panel highlights the head tracking, providing the 6 degree of freedom camera pose. Below that, the purple panel shows the hand tracking. This uses a key hybrid strategy. It combines precise 3D parameters like joint angles with a 2D projected skeleton to resolve depth ambiguities. These control signals are fed into the central diffusion transformer blocks, which use them alongside the context of previous frames to generate the next video frame step by step. So, while Figure 3 outlined the architecture, Table 1 provides the hard numbers that justify those design choices. It compares different strategies, listing methods that use only hand pose parameters in the middle, and video-based methods below them. If you look at the hand pose accuracy columns on the right, the parameter-only approaches clearly struggle with alignment. However, the bottom row confirms that the hybrid strategy works best, achieving the lowest mean per joint position error of about 12.2 millimeters. Okay, Table 1 established the best way to track hands, and now Table 2 adds camera control into the mix. It compares a camera-only baseline in the top row, a hand-only baseline in the middle, and the proposed joint control method at the bottom. The results highlight a trade-off. The hand control row shows a massive rotation error of over 13 degrees in the camera pose accuracy column, simply because it ignores head movement. In contrast, the joint control method in the bottom row bridges this gap. It keeps errors low for both modalities and actually achieves the highest video quality with a PSNR of 18.6. Alright, moving from technical metrics to actual user experience, Figure 7 presents the results from the human subject study. On the left, the task performance graph reveals a massive gap in usability. The red baseline bar shows a success rate of only 3%, indicating that text conditioning fails at fine-grained tasks. In contrast, the green bar for the proposed system jumps to over 71%. This advantage is mirrored in the right-hand graph, where users rated their perceived amount of control much higher, giving the hand-controlled system a score of over 4 compared to less than 2 for the baseline. Wrapping up, the big takeaway is that integrating precise 3D hand and head tracking into video diffusion models finally unlocks true interactivity. By moving beyond coarse text prompts, this system allows users to perform complex tasks with over 70% success rates. This points toward a future where immersive virtual worlds are generated instantly. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.